moving on, we have Fermat's theorem, and this gives us a mathematical approach to finding these maximums and minimums. And it says that if f has a local maximum or minimum at c, then, and if f prime of c exists, then f prime of c is equal to 0. And so let's see that in action. If f of x is equal to x to the third, then f prime of x is equal to 3x squared, and so f prime of 0 is equal to 0. But f has no maximum or minimum at 0 because if you look, it's going to get increasing on this side. It's going to be decreasing on this side. So it won't be an actual maximum or minimum in those values. And so when that happens, f prime of 0 is simply, or f prime of 0 is equal to 0, simply means that the curve y equals x to the third has a horizontal tangent at 0, 0 instead of a max or min. The curve crosses the horizontal tangent there, and so that's one thing that can happen. And then another one we have is the function f of x is equal to absolute value of x. Does this have a local and absolute max and min value? Yes, right? The minimum value is at 0. But remember, it's not differentiable at 0, so it doesn't have an f prime of 0. And so it's kind of a warning sign that example 5 shows that we do not require a maximum or minimum at c for f prime of c to exist, or equal to 0 to exist. And also there may be extreme values even when f prime of 0 does not exist. And so there's two kind of pitfalls we have to watch out for. And then we're going to get into critical numbers, and the critical number is the definition of a critical number of a function of f is the number c in the domain such that domain of f such that either f prime of c is equal to 0 or f prime of c doesn't exist. So it kind of adds on to Fermat's theorem in a way. And so let's find this critical number in this equation. So we've got x to the 3/5 power, times 4 minus x. So to do the derivative of this, remember this is the product rule, so we've got x to the 3/5 times the derivative of this thing, which is going to be just -1. And then we've got plus this thing times the derivative of that, which is 3/5 x to the -2/5. Okay. And then this is going to be negative x to the 3/5 plus, what is that, 12/5 x to the -2/5. Oops. So this is going to be -3/5. Okay, this is x to the 5/5 plus 2/5, so 3/5 x to the, minus 2/5. Okay. So what do we have? We have that's kind of gross. How can we do this? Negative x to the 3/5 plus how do we work this out? This is going to be, we can factor out x to the -2/5. So x to the 2/5 on the bottom. 5 times that, because that's in both of these. And it's going to leave us with, this is going to be, we could factor a 3 out. 4 minus x again. Yeah. maybe I shouldn't have foiled this out and distributed this to these two things. That's probably the better way to do this. Okay, and so then from here, we can get a common denominator. So we need to have 5x to the 2/5 on the bottom. And then we're going to multiply that by 5x to the 2/5 times negative x to the 3/5. And then we've still got all that other stuff, plus 3, 4 minus x. Okay, this is going to be negative 5. Oh, x, right? This plus this, yeah, that's x. Plus 3, 4 minus x. 5x to the 2/5. Okay. And then this is going to equal negative 5x plus 12 minus 3x over 5x to the 2/5. So this is 12 minus 8x over 5x to the 2/5. Okay, so now this is the derivative, right? F prime is equal to this. So where would this equal to 0? Well, this would equal 0 where 12 minus 8x is equal to 0. So we add the 8x. We have 8x is equal to 12. And we get x is equal to 3/2. Okay. And so f prime of x is equal to 0 when x is 3/2. And f prime of x does not exist when x is equal to 0, right? Because if we plug 0 into the denominator, we get a problem. But the critical numbers here are this x equals 3/2 and 0. Okay, so that's how you kind of go about this. It does take practice. You'll get better with it in time. And with that being said, I hope you guys are learning some things and getting better at your differentiation, because we do a lot of it in this class, and we're going to do a lot of integration too. So thank you guys for watching. We'll continue in just a second.